This talk I planned as an overview, so I have a long list of collaborators and long list of references. And this is my outline. I will first tell you my motivations about why QCD at finite density is interesting. Then I will give very brief review about neutron stars and holography and holographic models. Then I will tell you about finite temperature equation of state for QCD. Then I will tell you about how we can apply them to neutron star phenomenology. Then this section in the parentheses is tentative. There are the recent stuff that I am interested in. If I have a time, I will talk about exotic phases in QCD. Anyways, let me start with my motivations. I have two very strong motivations. And the first one is determining the phase diagram of QCD is a very challenging task. This is very important for theoretical physicists. And it is challenging because, maybe in the first place, I need to say that QCD is one of the fundamental force. It is the strong force that keeps the quarks and gluons inside hadrons. But the funny thing about QCD is actually the coupling constant is not a constant. It is running with the scale. And here we have a schematic phase diagram of the QCD. And in the vertical axis, we have temperature. In the horizontal axis, we have baryon chemical potential. And all the color patches are the available tools that we have to understand the QCD. And as I told, the coupling constant is running with the scale. When it is asymptotically large in temperature and baryon chemical potential, everything is okay. We can use our traditional perturbative QFT tool to understand that. And this red regime is the applicability regime for the perturbative QCD. Then we have this green regime, which is lattice QCD, which is the only first principle fundamental tool that we have. It works well for small baryon chemical potentials. Then we have this purple part, which I call this effective field theory, which is actually effective field theory with some hadronic degrees of freedom or some nuclear theory statistical models. Then we end up with this white patch that we don't have any available tool because it is the strongly coupled regime of the QCD. And it is very important because we have this dashed line here. This dashed line is the phase transition line between the nuclear matter and the quark matter. And actually, we don't know the nature of this phase transition. It can be first order. The only thing we know that at the zero chemical potential, it is crossover. And we don't know the properties of this phase transition, even the critical endpoint exists or not. These are open questions. And my second motivation is it is very timely and exciting to working on this subject because there is data and there are two different sources of the data coming. The first one is our old friend heavy ion collisions. In the second beam energy scan program, which is covering that regime, the data is already collected at RIC and it will be analyzed. And the main motivation for these experiments is just to probe whether the critical endpoint here exists or not. And if it exists, where is its location? This is the main question. And we have another source, which is coming from completely different field, astrophysics. If we want to understand neutron stars, then we need to go zero temperature for isolated neutron star, but we need to go really dense QCD, somewhere here. And if you want to understand the neutron star mergers, you need to heat up your system, because during the merger, temperature increases. So in this talk, I will focus in this regime. And this is my very brief review about neutron stars. I'm not astrophysicist, and the picture in my mind is very rough approximation. Neutron star for me is just a blob of QCD matter. And we don't know what it is actually. They are very exciting objects. Their mass is 1 to 2.5 solar mass, and their radius is from 10 to 15 kilometers, which means that they are super compact and dense objects. But the main problem is we don't know what is inside the neutron star, in the inner core of the neutron star. Normally, there should be neutrons, but there can be also quark matter, or there can be even more complicated exotic phases of the QCD, like paired phases, like color superconductor phases, or baryonic superfluid. We have no idea about that. And if you want to understand it, Again, with the rough approximation, the physics is simple. You have fermions, you have some Fermi pressure, which is competing against its self-gravity. So this is kind of hydrostatic equilibrium. And if you want to understand them in general relativity, you need to just solve TOV equations, which are Einstein's equations with hydrodynamics. And these are the equations. We have pressure here, this is energy density, and this is mass. And the thing about these equations, these pink boxes are the only input which encodes the underlying microscopic theory. It is the energy density as function of pressure. So it is the equation of state. It is the equation of state for the QCD. And the story is, if you know the equation of state for the QCD, you can plug it here, and it will throw out mass-radius relation for neutron stars. So the idea is, in astrophysics, they are able to measure the mass, radius, and the related parameters. And since there is one-to-one correspondence between equation of states, then you can use these measurements to constrain QCD equation of state. Okay, and the measurements for example, for the mass measurements, the maximum mass for the static neutron star should be higher than the 2 solar mass. And the other important measurement is from LIGO and Virgo gravitational wave observation, which says that there is an also upper bound for tidal deformability. And tidal deformability is a quantity which is roughly the measure of the shape deformation of the neutron star. I mean, if you are considering a merger, if you are considering a binary of a neutron stars, in the inspire phase, you can neglect the tidal forces, but just before merging, there will be a shape deformation, and this is the measure of it. And the nice thing is, these two lower and upper bounds are complementary to each other for QCD equation of states. And the thing is, the equation of state should be stiff, but not too stiff. It is very important, and what I mean by stiffness here is speed of sound. This is very important criteria because many models are failing about this. So, yeah, I just moved to gauge gravity duality, the model that I used to understand neutron stars. As I told in the beginning, I want to understand a strongly coupled regime of the QCD, and we don't have any available first principle tool. So we can use gauge gravity duality. This is kind of a model, but we know that it works well at the zero density. So we can hopefully think that, yeah, it can work for finite density. And gauge gravity duality, holography, or ADS-CFD duality, it is a duality between strongly coupled gauge theory, like a QCD living in 4 dimension, and weakly coupled gravity theory living in 5 dimension. And the best way of understanding it is GKB-Witten relation, which basically says that you have this kind of a space. You have a 5-dimensional bulk space, which is negatively curved, and you have some fields propagating inside of it. But on the boundary, you have a different theory, which is here you have the snapshot from heavy ion physics. And these bulk fields acting as an external sources of the boundary theory. In other words, we can say that the generating functions of the both theory is same. And if you know the boundary, if you know the generating functions, then yeah, you can take variational derivative and you can get the correlators. Okay, then it works well. And yeah, this duality works in some specific limits. The first one is number of the colors in the QCD should be large, which will reduce your action to on-shell action of the classical gravity theory for the strings. But you will also take the effective coupling large, which will get rid of all of the stringy corrections. So you just will have some classical theory of the point particles to understand QCD, but living in 5 dimension. And yeah, this is another artistic picture. I mean, we need a charged black hole solution living in a 5-dimensional negatively curved background. And we want to understand QCD phase diagram. And in the end, we want to apply them to neutron stars. This is the basic idea. And we need to consider some specific model, some holographic model, because At the finite density, we need quarks and baryons. In original ADS-CFT duality, you just have gluons. And to have any effect of the flavors, any effect of the quarks, you need also number of the flavors large. You are already keeping number of colors large. Then you have this ratio, which is invented long time ago, Veneziano ratio. And this ratio is actually measure of the back reaction of the flavor sector to a gluon sector. And the model that we consider is this, Veneziano QCD, and it has two building blocks. The first one for the glue sector, the second one for the flavor sector. And they are, yeah, this is one of the most sophisticated models in a sense that, for example, in the glue sector, we have asymptotic freedom, we have confinement, deconfinement phase transition, we have nice glue ball spectrum and nice finite temperature thermodynamics. When I say something nice, I mean it is consistent with the lattice QCD. And in the flavor sector, we have breaking and restoration of the chiral symmetry. We have nice meson spectrum and nice finite temperature hydrodynamics. So this model works well. And I will tell you about just the field content of the model. It's a little bit crowded. In the glue sector, in the pinky part, we have a dilaton field. We have some scalar, which is due to trace of the gluon field strength tensor. So the source will be the coupling constant of the QCD. So this field is actually blowing up in the IR to have a strong interaction, strong coupling. And we have a metric tensor, which is due to energy momentum tensor of the boundary theory. And also we turn on other scalar, and this scalar is also blow ups in the IR. And this is due to chiral condensate, so it actually mimics the chiral symmetry restoration and chiral symmetry breaking. And the source is the quark mass. And then we have abelian and non-abelian field. These IJ indices are flavor indices, so all of them are NF by NF matrices, and these gauge fields are due to this chiral currents. And with this field content, yeah, we still need some stuff. This is the whole action. I don't want to go in too much technicalities, but what I want to emphasize here is these functions. We have some potentials depending on coupling constant. And the idea is these functions are the buttons or knobs that you are tuning with the QCD features. I mean, the idea is they are function of dilaton, so they are function of coupling constant. In the first place, I can fix their asymptotics at the weak coupling with the perturbative results, like running off the coupling constant or running off the quark mass. And on the other hand, when there's a strong coupling, I can fix the asymptotics with the strong coupling features, like chiral symmetry breaking or confinement deconfinement phase transition. And in the end, you need to interpolate between these two ends. And for that, we are just using lattice results. Let's just focus on this plot. The red bars are from the lattice and the blue curves are from the model, VQCD model. And this is the interaction measure, which is energy density minus 3 times pressure, which is the measure of the deviation from the conformal theory. And the thing is, this set of the curves is just coming from choosing different parameters. The thing that I want to emphasize here, we have these parameters. You may say that, yeah, you can play with the parameters, you can fit with the elephant or whatever, but the thing is actually, this fine tuning only leads this change in the curves. This bump is always there, which is the first and foremost prediction of the VQCD. So it really mimics the QCD. And these functions, these potentials are just simple monotonic functions. They are not artificially tailored functions. And with these models, we have this kind of a phase diagram. We have a confined phase, we have a deconfined phase, but we still need something. We need baryons. And baryons is, in holography, it is very difficult subject because they are the solitonic configurations of the non-abelian gauge fields, which is extremely difficult problem if you want to deal with several baryons and interactions between them. But actually you don't need to solve it because you can make some ansatz. In the first slide, I show that we have effective field theory. At the low density part, we can use it. And in the high density part, which is homogeneous nuclear matter, you can make it this simple ansatz, which will be just an homogeneous field with some flavor indices. Then you're able to solve it. But you need to match with the low density theory. And if you do that, and if you want to use this to understand some neutron star physics, this is the mass radius curve for some specific event, the event GW 1908-14. And this event is merging event between a 20 solar mass black hole and some light companion. And this companion is unidentified because it is falling into mass cap. It is too heavy to be a neutron star and too light to be a black hole. But if you give these are mass radius relations, and these are the allowed neutron stars in your theory, and you want to reach this green ribbon here, if neutron star can achieve 2.5 solar mass. And the thing is, actually, we simulate this and we see that if it is really fast rotating neutron star, then it achieves this band, which means that maybe this unidentified companion in this gravitational wave event can be a neutron star, because the equation of state is stiff. And then we consider finite temperature generalization, because in the end, if you want to understand neutron star mergers, as I told, you need to heat up your system. And this is the construction of our model. All the red parts are coming from gauge gravity duality, all the deconfined phase, quark matter phase. And you have zero temperature nuclear matter phase that I tell you. And we need to extrapolate it somehow. And we just use very simple model for that, which is just Van der Waals model for hadronic gas. You are just adding some excluded volume correction and some attractive interactions. Normally in nuclear theory, this model is, parameters of this model is chosen by phenomenology, but in this case, we are using the parameters of this model to fit with the holographic result at the zero temperature, and we extrapolate that. And then you have a whole model covering all the phase diagram of the QCD. And you have a phase transition, which is very important thing. And then, this is the result for the phase diagram here. I mean, we have again temperature and baryon number density here. And we have these two solid curves, which are phase transition lines. In between, there's a mixed phase. And on the left, we have nuclear matter. On the right, we have quark matter. And these two lines, phase transition lines, are ending on this yellow star, which is the prediction for QCD critical endpoint. And the colors are the speed of sound, which is well above 1/3, which means that it is very stiff. And I only want to stress one thing. These are the variants of the VQCD models, and this is one widely used nuclear theory model. And these three columns are the predictions for the QCD critical endpoint. The thing is, in the nuclear theory, it is left blank because they don't have phase transition. In many traditional nuclear theory models, they don't have phase transition in a single framework. Okay, this is the advantage of the holography to use it. And then, this is the equation of state. I need to say a few words. This orange band here is the constraints coming from nuclear theory. And the other one is the constraints coming from the perturbative QCD. And this blue sausage-like shape is all the feasible equation of states with the polytropic extrapolation. And all the dashed curves here are widely used nuclear theory equation of states for the QCD, and they all going outside this blue sausage. And these solid lines here are coming from the gauge gravity duality, which are still going inside the constraint of the perturbative QCD. And the other thing is we have this plateau here, which means that we have a phase transition. And you can investigate the features of phase transition in neutron stars. And then after constructing up this finite temperature equation of states, we implement neutron star merger simulations. And let me say a few words about the scenarios that we have. The scenarios first depend on the mass of the companions in the binary. If it is large, like 2 solar mass, then these two neutron stars just collapse into a black hole with torus, which is accreting onto black hole. And in that case, the gravitational wave signal will be something like this. You have this oscillatory part, which is in spiral phase, and in the maximum they merge. Then the signal terminates because it is just promptly collapsing into a black hole. What is interesting is if you are considering a lower band, if the mass are small, then again they are in an spiral phase, but they will form some supermassive neutron star as an intermediate step. And depending on the initial condition, they can either collapse into a black hole or a neutron star, isolated neutron star. In that case, the waveform will be different. There's a post-merger part of the signal. And this post-merger part is very important because it tells us about the phase transition. And in the LIGO and Virgo right now, they're just able to see this part, in spiral part. But in the future, when the sensitivity increase, they will also see this post-merger part, or in the Einstein telescope. So these are the scenarios, and we implement them with some big simulation. And but the question that we are after here, very clear, well-defined question, whether phase transition from nuclear matter to quark matter really possible in the neutron star mergers. Nobody knows. And if it is possible, then what is the cleanest imprint of this in the gravitational wave signal? These are the questions that we are trying to answer. And yeah, this is the animation for the neutron star simulation. What you see is two neutron stars rotating about the z-axis. And this is the simultaneous waveform. At the t0, they will merge. And you are in the post-merger part of the signal. Okay? And the question, and it is collapsing into a black hole. And the question that we ask, phase transition, and we will just zoom in this. And in this case, after the merging event, you will see some annuli inside this center of the merging plane, some dashed and dotted annuli, this one. And these are the regions where you have quark matter formation. And just after that, it will collapse into a black hole. And this is the prediction of the holographic model, because in the deconfined phase, in the quark matter phase, it is not stiff enough to support a stable neutron star. So the cleanest imprint will be something like this. I can skip this one. Yeah, let's focus on this. With this simulation, you can analyze the gravitational waveform, power spectral density, and spectrogram. But let's focus on these two. The first one, when we take out the quark matter phase, so phase transition artificially. The second one, when there's a phase transition. And if you just compare this, yeah, you will see that there is an early termination of the signals. And this is because it is just collapsing into a black hole, because quark matter is too soft in holographic models. This is the prediction of it. And you can also compute the characteristic frequencies, and you can compare with the data, etc. Okay, yeah, this is more or less what I want to say about merging events, and I think I still have time. Okay, very good. Yeah, this is one of the things I recently focused on. As I told, this quark matter phase can be some exotic phase. And you can use holography to understand that. In the first place, in holography, if you want to mimic QCD, there are global flavor anomalies of the QCD, which dictates some Chern-Simons term, some unique Chern-Simons term in the holographic theory. And it is well known that these will lead some instability in your model. And people look at these, at the top-down models, and they are very irrelevant for the neutron stars or heavy ion collisions, because they are at very high density and very low temperature. Then we investigate these with our model, and we see that this instability regime, which is this colorful regime, and these are the phase transition lines again, actually it exists at the very high temperature, even okay for heavy ion collisions, and at the very low densities. This is very surprising thing. And of course, yeah, this is just a model. Then we were just after this paper, we focus on whether this property is model independent or not. And we will look at class of models. All of them are bottom up, but all of them are some fitted with different strategies. They are fitted with the lattice QCD. I mean, and this instability is always there. I mean, which means that, yeah, very interesting in a sense that, I mean, you have spatial modulation in your deconfined phase. And it is something like chiral density wave, but not exactly the same because there isn't any chiral condensate in the system. But there is some spatially modulated chiral current in your plasma. And this may affect lots of things. It may, for example, change the thermodynamics. It may make the quark matter equation of state stiffer. But we don't understand it very well. But we show that it is modally independent property of any holographic model which is fitted with the QCD lattice data. So this is one of the things which is interesting, but we still don't know much about this because we didn't construct the ground state of it because it's numerically expensive. But this phase is also in competition with the other exotic phase, which is color superconductor phase. And yeah, we are also working on this recently, and this is actually, I don't want to say much worse about this, but you expect the color superconductivity at the large chemical potential regime of the QCD because quarks have Fermi surfaces, there's asymptotic freedom, and also the interaction is very weak. And what you expect is, yeah, you can add a pair without cost. And if you have any attractive channel, then they will lead up some pairing, some Cooper pairing in the system. But we don't know still much details of it. And I think it's all. And I can skip the recap, but I can say a few words about the outlook. What we see is these holographic models don't have flavor dependence, and it can be very important for unstable phases. We are after that, and we need to determine MHD, magnetohydrodynamics for quark matter to improve the simulations. And also this competition between the exotic phases, spatially modulated phase, and also color superconducting phase, it is one of the important things because we understand which one is dominant. And the take-home message is gauge gravity duality combined with the other methods are extremely useful to study QCD since it accommodates strong coupling effects and phase transition. And yeah, that's all. And I have picture here from very long time ago. I even have hairs. I'm very young. I'm at my undergrad years. And I was very lucky to meet with the Durmuş Hoca. And he impacted my career very early. And many other people impacted my career, but he was kind of very special because he was the first one who sparked and triggered this excitement about the physics. Okay, yeah, that's all. I think I'm done.
Thank you very much. Yes, we can have several questions.
Do your calculations indicate stable neutron stars with a quark phase present at the center?
No.
Not even for low masses.
No, it always collapses, but there is missing pieces that I told you about. I mean, we right now don't have any flavor dependence, but you need to include them. And we know that it suppresses some features of the equation of states. Then in that case, yeah, your quark matter equation of state can be stiffer. And also for the paired phase, it can be stiffer. It is still ongoing investigation. But right now we can say that in this model, yeah, it is not possible to have a just quark matter inside the core. You can create it, but it will promptly collapse into a black hole.
Any other questions?
I have two questions. Have you considered neutron star black hole mergers?
No, we haven't.
Because there are observations of that.
Yes, yes. I mean, we considered we didn't perform simulation for that, but I mean, for this mass radius relation, it is actually somehow related with that. I mean, this event is an maybe black hole and neutron star merger, but we don't know the second companion. But we are speculating that the second companion will be a very fast rotating neutron star. Otherwise, it is not possible to, because this centrifugal force also gives extra contribution to support more mass for neutron stars. But right now we just only consider this, and this is not a simulation, this is just, isolated rotating neutron star, simulation for just a rotating neutron star, not a merger.
And the second question is about the electromagnetic signature of this neutron star mergers or neutron star black hole.
Yeah, it is a good question. I mean, because, this gravitational waveforms always sometimes comes with the electromagnetic counterpart. But what I want to show you, the outlook. I'm not a simulation guy, I'm a theory guy, but in the simulations, they are at the primordial stage in a sense that they even don't have dissipation. I mean, they have some effective dissipation, but you are not putting, for example, viscosity or any other dissipative terms. And electromagnetism is definitely needed. But I mean, this is the region that I write down we need some causal magnetohydrodynamics to understand it. But it is at the same time numerically and also money-wise very expensive thing. I mean, these simulations are a really big thing. But they are in the agenda of the simulation group for sure.
Okay, since we are running short on time, we can postpone the other questions to the coffee break. And thank you, Tuna.
Thank you.
For this nice talk.